Hello and welcome to my presentation on the tower winch system I designed for my ham radio station. Please note the disclaimer statement at the bottom of the slide. I am not a civil engineer. I'm simply describing how I designed my own system as a hobbyist. Consult a professional engineer if you have any questions or concerns regarding the safety of people or property. I'd always wanted to install a tower and put up real antennas. After some research, I settled on the Universal Towers HD21-50 freestanding tower. I chose a freestanding tower because I didn't have a great way to support a guide tower without creating obstructions near the driveway. Also, I didn't want a tower that required climbing for antenna installation and maintenance. The picture on the right shows the assembled tower system, consisting of a hex beam, 5-element 6-meter beam, a VHF-UHF Yagi, and a wideband discone antenna. The directional antennas are mounted on a 16-foot mast with about 10 feet of exposed length at the top. A thrust bearing was installed on the top plate of the tower to minimize stresses on the rotator. The Universal Tower products are freestanding designs with a large concrete footing at the foundation. The mass of the foundation acts as a counterweight for the tower. The entire tower can be lowered by removing one set of mounting bolts and relying on the other set of bolts to serve as a hinge. This avoids the need to climb the tower or rent a portable lift to perform maintenance. To keep the tower from lying flat on the ground, I used two DX Engineering Genius clamps, a galvanized water pipe, and two pieces of 2x4 wood to form a standoff leg configuration. The wood legs free swing, rotating to the vertical position as the tower is lowered. The rightmost picture shows the tower standing up with a galvanized pipe crossbar located about 18 feet above the ground. While I had a good idea where I wanted the tower to be sited and how the antennas, masts, and cables would be installed, I really didn't give much thought to the winch system design. The tower itself weighs just under 200 pounds, so I thought a 1,200-pound brake winch would be more than adequate to handle the load presented by the tower and antennas. Also, the snatch block configuration would help reduce the force applied to the winch by a factor of 2. After a trip to the hardware store, I purchased an 8-foot long 4x4 post and 2 bags of cement to set the post. The post was set 3 feet in the ground, leaving 5 feet above ground level. The picture shown was from an early test with only 2 sections of tower installed. Well, trying to wing it by buying a bunch of hardware and putting it together proved to be, as you might suspect, the wrong approach. I really should have done the proper calculations to figure out the forces on the cable and the load requirements of the brake winch. The 10-degree starting elevation, the low height of the winch post, and the low cable attachment height on the tower led to a winch system that was wholly underrated for this application. The problem was so bad that I needed a neighbor to bring in his tractor to help push the tower up while I cranked on the brake winch. As the saying goes, live and learn. Based on this failure, I came to realize that I really needed to compute the forces on the winch cable system before trying to build a replacement system. Using physics and trigonometry, it was possible to come up with a set of calculations to determine the forces on the winch cable and the winch post. At each position and elevation, the system could be considered static and in equilibrium. In equilibrium, the sum of all the forces equals 0. Likewise, the sum of all the moments, or torque, on the system can also equal 0. Everything balances out and the entire tower system remains stable for any given elevation angle. To assess the forces on the cables, it is necessary to know the distance from the point of rotation, or the hinge point, and the magnitude and direction of the forces. An arbitrary force F, applied at a distance r from the point of rotation, creates a moment or torque on the hinge. More specifically, only the perpendicular component of the applied force at the distance r produces the actual moment. Any force parallel to the axis of the rigid body does not contribute to rotation and instead represents compression or tension of the rigid member. In our application, this would equate to compression or tension of the tower. The formula at the bottom shows the moment m is the product of the distance r times the perpendicular component of the applied force. To compute the parallel and perpendicular forces on the rigid body, it's necessary to use trigonometry. In the example shown, force F is resolved into two components, F perpendicular and F parallel. F perpendicular is equal to F sine phi, while F parallel is equal to F cosine phi. The moment around point A is r times F sine phi. To compute the system's forces and moments, it's necessary to draw a free body diagram. The green line represents the tower, and the purple line represents the mast. The red line represents the winch cable attached to brackets at point B. The winch cable passes over a pulley at point C, mounted on the winch post. In this system, the winch is installed on the winch post, and the winch cable is routed vertically along the post and over the pulley. The tower hinges at point P. W sub T represents the weight of the tower concentrated at the center of gravity point. For worst-case analysis, the weight of all the antennas is concentrated at the end of the mast and represented by W sub A. Note that the winch post is offset from the hinge point by distance L1. The perpendicular force components, at right angles to the tower and the mast, create the moments experienced at the hinge point. The parallel force components, along the line of the tower and the mast, represent compression and the force applied to the hinge hardware. Since the winch post is offset from the hinge point by a distance L1, it is necessary to compute the interior angle phi between the winch cable and the tower at the bracket attachment point. The law of cosines formula was used to determine angle phi. The winch post utilizes backstay cables and ground anchors to stabilize the post during winch operation. The backstay cables reduce the bending stress on the winch post, preventing it from splitting or snapping at mounting point E. In this free body diagram, force F1 has the same magnitude as force F sub B in the previous diagram. Force F2 represents the tension in the backstay cables. The winch post is kept in equilibrium when the perpendicular components of F1 and F2 have the same magnitude. Note that the parallel components of F1 and F2 are directed downward. Most importantly, these force components are directed along the winch post itself, representing a vertical load on the post. Although the post may not sway to the left or right in this diagram, the post experiences compression due to the downward directed components. For the winch post, the vertical load rating should be used when selecting the proper post size and material composition. A top-down representation of the site is shown in this figure. In the original plan, the two backstay anchor points were intended to be symmetrically aligned with the winch post and the tower. However, an underground obstruction forced the two anchor points to be shifted from the center line. So long as the backstay cables remain in tension and counteract the winch cable force, the winch post will not sway to one side or the other. The winch post selected for this application was a 16-foot long 6x6 pressure-treated post set in concrete. The height of the post above ground was 12.5 feet. The tower is constructed from aluminum tubing, necessitating the use of stainless steel hardware to avoid corrosion due to dissimilar metals. For this application, it was necessary to have custom stainless steel brackets fabricated by a local machine shop. The brackets are attached to the tower using stainless steel U-bolts. 2 brackets are used, attached to the 2 legs associated with the hinge arrangement. The bracket and cable connection configuration is shown in this figure. On the left side, several flat washers had to be stacked at each U-bolt leg to produce the equivalent of a through-hole standoff. This standoff configuration ensured that the associated hex nut would remain on the threaded portion of the U-bolt leg and allow the bracket to be tightened against the tower leg. On the right side, the top-down view shows 2 brackets mounted on the tower legs. A yoke configuration, constructed from 1/4-inch aircraft cable and a shackle, was used to connect to the winch cable. The 2 ends of the yoke cables attached to the brackets using quick links. The 180-degree slot in each bracket allows for minor length differences between the 2 yoke cables, as well as any offsets in the center line between the tower and the winch post. Using 2 brackets at the rearmost tower legs minimizes the stresses induced on the tower zigzag bracing and welds during lifting. The sketch provided to the machine shop is shown on the left side of the figure. While 1/4-inch thick plate is most likely overkill in this application, the cost savings using thinner plate material would have been minimal for this custom job. The U-bolts and quick links are shown on the right side of the figure. Using the free body diagrams, a spreadsheet was used to compute the parallel and perpendicular forces in the system. Input parameters were entered into the yellow cells. Computed results were displayed in the tan cells. To avoid a divide by zero condition in one of the cells in the spreadsheet, a maximum elevation angle of 89.99 degrees is used instead of the theoretical value of 90 degrees. For the as-built tower and winch post system, the forces in the cables and posts were computed as a function of tower elevation angle. The tower system starts off at a 10-degree angle. At the start of the lifting process, it is informative to see just how much force is present in the winch cable and in the winch post. The parabolic shape of the backstay cable forces was equally informative, showing that the system is experiencing significant changes near 35 degrees elevation. It should be noted that, for a shorter winch post, the winch cable and winch post forces become even greater. This explains why the original winch system, with its 5-foot post height, failed to work with the hand-operated brake winch. The moment or bending stress on the winch post similarly peaks around 35 degrees elevation. This information can be used to determine if the winch post material can withstand the stresses induced by the lateral load forces. Well, I learned my lesson. It's necessary to compute the forces in the cables and other structural members before purchasing any materials. If you wish to learn more about this project, you can download the documentation and the spreadsheet and watch a video of the tower being raised using an electric winch. I'll put the Dropbox link in the comments. Thank you for watching.